Hello everyone, I'm Hongwei Zhao and this is my project Star Detection with Deep Convolutional Neural Network. Introduction. The star tracker is the most accurate attitude sensor available for spacecraft. It is essential for all kinds of space missions, including laser communication. Historically, star trackers are very large and very expensive, but recently several low-cost nanostar trackers have been developed, such as the ST16 nanostar tracker here. The image sensors used by this nanostar tracker are not very sensitive. Therefore, it is very challenging for them to detect dim star of the high rotational rate using conventional threshold method. Therefore, a deep convolutional neural network approach is proposed in this project to perform star detection. To train a neural network, one has to obtain training images and corresponding label first. Therefore, a star image simulator is developed. The Hipparcos catalog is used. The stellar aberration is considered. With the magnitude information from the catalog, the photon counts can be calculated. The defocusing of the optics is simulated by a 2D Gaussian distribution. The receiving of photon by the image sensor follows a Poisson distribution. When the satellite is rotating with non-zero angular velocity, the star image won't be a point, it will be a smear. This is simulated by generating several sub-images with very short exposure time independently and stack them together to generate an output. The quantization is performed on this output and is stacked with a noisy background, illustrated here, taken by a real camera connected to the computer. The star detection can be considered as a binary segmentation test, where if this pixel has star signal, it should have value 1, otherwise it should have value 0. The UNet has demonstrated very impressive performance on all kinds of segmentation tests and therefore is used in this project. Only the first 3 blocks or the first 3 max pooling are taken from the UNet. The reason behind this decision is that the stars are very smart objects, and therefore too many max pooling will be unnecessary and might even lead to a failure of star detection. Batch normalization are added after each nonlinear activation function, except the last one, to provide regularization. Because this is a binary segmentation test, the sigmoid activation function is added to the end of the output. The binary cross entropy is used as the loss function. The input to the network is the raw noisy image. The output of the network is the segmentation map. Here is the ground truth segmentation map provided by the star image simulator. Now let's look at the experimental result. 300 images are used for training, 100 for validation, and 100 for testing. A common adaptive threshold method is also implemented to generate a segmentation map as a comparison. The intersection over union is used as the metric to evaluate the performance. The performance of both methods on the 100 test images are shown here. The DCNN, Deep Convolutional Neural Network method, outperforms the adaptive threshold method by a large margin. The advantage of DCNN method can be further illustrated on the images here. The pixel with white color represent it is detected by both DCNN method and the adaptive threshold method. For those stars that can be detected by the threshold method, the DCNN method can not only detect it, but also detect the boundary pixel of the stars. And the yellow colors means it is only detected by the DCNN method. On the second row, we can see there are some very dim stars that are only detected by the DCNN method. We can make the threshold method more sensitive, but it will also generate lots of fake detection, as can be seen on the third row represented by blue color. In conclusion, a star image simulator is developed. A deep convolutional neural network approach is proposed and outperforms the conventional threshold method by a large margin. In the future, it will be necessary to further optimize the network structure to be used in flight hardware.